In this video we're going to talk about the symmetry of functions. So there's two different types of symmetry we're going to look at. First one is what we'll call an even function. So a function is even if f at negative x is equal to f at x for all numbers x in the domain of f. What does this mean? Well, it's easier to see why we call this a symmetric function when we look at a graph. So let's think about a function. And what I'm going to do is I'm going to draw a function just on the positive side. So it'll look something like this. So what this rule here is saying for even functions is that f at x must be equal to f at negative x. Well, let's think about a value of x. So if this was x, well, the negative x would just be right over here on the negative side. Right? Whatever, if this was 5, this would be negative 5. Well, these two values, this is f at x, must be the same as over here. So this point here must be mirrored over here. And that's true for all the points. So what you end up happening is sort of a mirror image. Let me do my best to draw this. So that's not exactly symmetric looking, but basically this side should look the exact same as this side. So that's what we mean by even function. So it's symmetric sort of about this line here. Right? We get a mirror image. So this means the function is symmetric about the y-axis. So every point here is matched up with a point directly opposite on the other side of the y-axis. So you end up with kind of a mirror image, which is what this means over here. Whatever x is, negative x, f at negative x has to be the same. Okay. Okay, and the second type of symmetry we're going to look at is what we call odd functions. So a function is said to be odd if f at negative x is equal to negative f at x for every number x in its domain. So this one's sometimes a little bit trickier to see how it's symmetric. So sometimes to sort of see how the graph works for this one, I'll just rearrange this equation. So I divide both sides by a negative. So I'd end up with f at x is equal to negative f at negative x. So hopefully you can see that these two equations are the same. I've just rearranged the negative. I've just rearranged. You could think about it, I just kind of switched their sides. So how does this work? Well, again, I'll draw the function on one side of the axis. So let's draw it something like this. So let's say this is our x value. So f at x is down here. So what this rule tells me is that f at x, this point here, must be the same as negative f at x. So if you think about transformations, what that means is we have a transformation, a reflection about the x-axis, or sorry, about the y-axis, and then about the x-axis. So I'm going to take this point, reflect it about the y-axis, it goes over here to negative x. So I'm here, but then I reflect it up about the x-axis. So I'm here. So whatever this height is negative, this height is positive. So you're saying, well, where's the symmetry there? Well, the symmetry is it's symmetric through the origin. So the origin is right here. What this means is symmetry about the origin means if I were to draw a line from this point to the origin and then continue that line, I would continue that line the exact same distance until I get to this point here. So this line should be the same as this line. It's just a straight continuation. And the way you get the rest of the graph is you just continue to do that. So let's say I wanted to find the symmetric point here. I draw a straight line to the origin, and then I would just continue that straight line. So it should be a straight line, the same distance, and I'd be about here. Okay. And you're just going to continue that. So what ends up happening is, if you did that for a bunch of points, you'd see that it looks something like this. Okay. So you get kind of, it's like a mirror image twice. It's like you take this thing, reflect it in the y-axis, boom, and then you flip that and reflect it in the x-axis. So the way we say it is it's symmetric. Two M's. Symmetric about the origin. And another way that sometimes it helps people to think about it is it's a reflection about the x-axis and the y-axis. So if basically if you took half the graph here, reflected it once, and then reflected it again, you'd match up with the second part of the graph. So thinking about it either of these two ways can help you determine if a function is odd just by looking at the graph. Okay, so those are the two types of symmetry. We've got even functions, reflections about the y-axis, odd functions, reflections through the origin, or sorry, symmetric about the origin, but reflections about the x and y-axis. Sometimes we want to determine if a function is symmetric, but without using the graph. So we want to determine if functions are even, odd, or they might not be symmetric at all. So there we just say neither. So it's possible that a function, in fact, it's common that a function is not even or odd. So our first one will be the function f at x equals x squared plus 5. So how do you check if this is symmetric, even or odd? We'll go back to the definitions. Right? We had this definition for odd. So notice that the definition says, if f, what is f at negative x? If it's odd, then f at negative x is negative f at x. And for even, we had, again, f at negative x, but then you get f at x. So what we're going to do is just substitute negative x into the equation, or evaluate the function at negative x. So it's fairly easy to do. You just take negative x and just substitute it into this. So negative x squared plus 5. Well, negative x squared, you should know that's the same as x squared plus 5. Now hopefully you notice that this is the exact same thing as this, which means this is f at x. So f at negative x, right, is equal to f at x. Well, that's the definition of one of our types of symmetry. That's the definition of an even function. So therefore this function is even. Can do the same thing with another example. Let's say f at x, actually let's not use f all the time, let's say g at x. So it'll be the same definition, just instead of f's, now g's. So this one's going to equal, let's say, 1 over x cubed minus x. So the way we're going to do this, we're going to do the exact same thing. We're just going to evaluate this function at negative x. So if you ever want to determine symmetry, this is what you do. Just evaluate it at negative x. So negative x all cubed minus negative x, which would be 1 over, so negative x cubed. So it's a negative number cubed. Well, that's going to be negative. And then a negative times a negative would be positive x. So it doesn't look quite like this, right? These aren't the same. But notice there's a negative in front of this one. So usually we don't like a negative at the beginning. So let's factor out a negative sign. So if you factor out a negative, then this becomes positive, and then this plus x will become minus x. And notice that in this bracket here, you've got exactly what we had up here. So there's just a negative in front of it, which means negative g at x, which was equal to this thing here, which is just g at negative x. Well, that's the definition, again, of one of our types of symmetry. That's the definition here of odd functions. So therefore, this function is odd. And let's just do one more example. You can probably guess which type this one's going to be. Let's go back to f. So x squared plus 5x minus 1. So again, we'll evaluate it at negative x. So negative x squared plus 5 times negative x minus 1. Well, negative x squared is x squared. 5 times negative x is negative 5x minus 1. So now you check back to this one. Are these the same? No, they're not the same. They're close, right? But the difference is this negative sign here and this positive sign here. So they're not the same, and they're not negatives of each other, right? I couldn't just factor out a negative sign and then that wouldn't be the same as this. So it doesn't get us back to the original in any way, or the negative of the original. So therefore, this function is neither odd nor even. So this one is not symmetric in any way, or it doesn't any of our types of symmetry that we're looking at. Okay, so that's an option, and that these three examples show you how you check for symmetry. Just substitute in negative x, and if you get back your original, even. If you get back your original with a negative in front of it, odd. And if you don't get back either, like it's not your original at all, it's not even or it's not odd.